Alright, hello everyone. My name is Jiawei. I'm from the Medical Robotics and Equipment Lab from University of Maryland, following the Dr. Axel Krieger. My research topic today is landmark-guided deformable image registration for supervised autonomous robotic tumor resection. Let's start from the research background. The tumor surgery in head and neck region. Oral cavity cancer and oropharyngeal cancer are the two most common cancer occurrences in the head and neck region. They account for a large number of new cases and deaths worldwide. And as the most common variants of the oral cavity and oropharyngeal cancers, the squamous cell carcinoma has the following features. The OSCC, the oral SCCs are superficial and controlled by complete excision. As you can see from the image 1 on the top left corner, top right corner, it says how the oral SCC looks like, and image B shows the CT images of the OSCC. And the surgeons will rely on the visual cues from the image A and the preoperative images on the image B to generate the surgical plan for the resection. And image C shows how it looks like of a removed tumor bulk, and image D shows how the oral cavity looks like after the tumor resection. And the tumor margins is the paramount thing you want to control because it directly impacts the clinical outcomes. If you cut too much, you impair the post-surgery organ functions. If you cut too little, tumor recurs. And tumor resection is performed using either open or endoscope or robotic techniques. For the robotic techniques, we always call them the transoral robotic surgery or TORS. It's already a very prevalent minimally invasive therapy for the oral SCC removal. As you can see from the image, it's a Da Vinci robotic system. There's a surgeon seat in front of the surgeon's console, controlling the two robotic arms under the vision scope, and all his motion will be replicated and transferred to the patient side, and the robot will do the operation directly to the patient. And I want to let you know this surgical resection is not done by a regular surgical knife. It's done by the electrocauterization. That's the primary treatment surgeries today, strategy today. The electrocautery tool can look as a scissor or a hook or a spatula. The robot system provides surgeons with a lot of advantages, including the high dexterity tools, motion scaling, and hand treatment filtering. However, it's not perfect. There are still limitations, and those limitations triggers our motivations of this research. There are three major limitations of the oral cancer resections. First is the marking strategy. As I mentioned before, surgeons rely on the visual cues and preoperative images to generate the surgical plan. However, besides that, they will use the India ink, showing the image C. They will use the India ink, those black ink, to tattoo the border of the tumor to help them to delineate tumor tissue and healthy tissue. However, this black ink are easily obscured by the blood intraoperatively and also the charred tissue. I have the image D to show how a charred tissue looks like caused by the electrocautery. This electrocautery is good because while it's cutting the tissue, it will also stop the bleeding. But there's a side effect of it. It causes this black powder which will obscure the current clinical marking strategy. What's more, there are errors coming from the surgeon's prediction of tumor bed position as well. Between the diagnosis and the actual resection surgery, surgeons will run chemotherapy or radiotherapy or chemoradiotherapy to control the tumor metastasis. But while they're doing it, the tumor shrinks and migrates preoperatively, and also the tumor shapes changes, deforms intraoperatively as well. There's no way for the surgeons to perfectly predict the tumor bed areas. Lastly, the third limitation, surgeons will feel tired after long hours operations. which leads to the inconsistent surgery result. So firstly, we aim to precisely track deformed shapes over weeks. So if we can do that, we can track the tumor shape, the deformed tumor shape, even after the chemotherapy, even after the tumor shape changes. What's more, we want to prove the feasibility of autonomous robotic tumor resection. The robot will never feel tired. It will always give us the consistent result, even over a full disk operations. Method 1, first allow me to introduce our medical robotic system to you, which is mainly comprised of 3 components. The first component is, of course, the robotic manipulator. We use the 7-degree freedom KUKA LB med arm. And the second component is a laparoscopic monopolar electrochrometry tool, which is mounted on the flange of the KUKA arm. And 3, the third component, dual camera system. We have an RGBD camera to capture the point cloud surfaces of the target tissue. Besides that, we have an external near-infrared light source and a near-infrared camera to excite and capture the near-infrared signals respectively. I'll explain that why we need them in the next slide. The marking strategy. As I mentioned, the current marking strategy is use the India ink, which are easily obscured intraoperatively by the blood and charred tissue. So we want to use something that will not obscure by those things, blood and charred tissue, which is the near-infrared marker, near-infrared fluorescent marker. We developed this near-infrared fluorescent marker by mixing indocyanine grain powder and cyanoacrylate and acetone. It looks like those grain solutions in the image. And after, if we shoot some external near-infrared light source on it and capture it using the near-infrared camera, the right image shows how the solution looks like. It gives us a very good signal-to-noise ratio. And those solutions can be dispensed with syringes to the targeted tissues. Once it contacts water, it will quickly harden and maintains its position for at least 6 weeks. Imagine we have a tumor shape. We select the tumor shape. It's a T2 OSCC tumor shape, and we draw this tumor contour on a pork tongue, a porcine cadaver tongue, to regard it as the pseudo-tumor. And if we also dispense the near-infrared solution, marker solutions evenly on the contour, those will be how they look like in the color images and near-infrared images. So this near-infrared fluorescent marker has features of strong tissue penetration. It will not be interfered. I don't know what happens. So it will, those near-infrared markers will not be interfered by the blood and charred tissue, and it gives us high signal-to-noise ratio, and it has durability and biocompatibility. After the method 2, we know we provide another marking method rather than the India ink to mark the tissue, mark the tumor. But how can we track the tumor after it deformed? We use the deformable image registration method based on the elastic body spline. But generally, it creates an elastic body mechanical model based on the Navier equilibrium partial differential equations. It's a landmark-based registration method, and it requires some manual near-infrared marker pairing. I'll use the images on the right side to show how this method will work with our markers. First, prepare the samples. We got some pork tongue samples, and we drew the pseudo-tumor contours and dispense the markers evenly on the contours. And then we cut a hole, and then close the hole again by this purse string suture technique to imitate the tumor migration. And also we pull the tongue tip to imitate the intraoperative tongue deformation. And the image D shows how the image A looks like in the near-infrared images, and the image E shows how the C looks like. So this method will warp image D to match the coordinate system in the image in the image E. So the image F is the registered image and also the registered tumor bed. We didn't implement this algorithm by ourselves. This algorithm is already being integrated into the inside segmentation and registration toolkit. It's a very famous toolkit in the medical image processing area. And after that, we register the deformed tumor shape, and then we want to integrate this proposed marking and tracking algorithm into our robotic system. We first give the image F, give the pseudo-tumor contour in the image F offset, a 5 mm margin to adequately resect all the diseased tissue. It's just a clinical standard. And then we overlay the waypoints from the 2D near-infrared images in the image G to the 3D point cloud points captured from the RGBD camera, and then we generate the incision path shown in the image H. And then this path is converted to the joint space trajectory via the KDL library, and then a low-level controller is implemented using the Iowa stack, ensure the robots follow the trajectory. So we realize the robotic resection. We have two different experiments. The first one focuses on the accuracy evaluation and comparison of the registration method only. In one, we want to determine the number of markers that needed to predict the deformed tumor shape. And then M2, we want to calculate the registration error of using different registration methods, deformable and rigid registration, and also surgeon's manual prediction. The steps are listed below. First, drew contours on the pork towns and dispense the markers. Then simulate the tissue deformation, tumor shrinkage, and we register the tumor bed contours and compare the difference between drawn and predicted contours. The drawn contours are like the ground truth of the deformed shape. I just use these images to set an example. We have original tumor, how they looks like, the pseudo-tumor, how it looks like in the image A, and then we imitate the tumor shrinking and tissue deformation. It's the image B, and in the image B, the contour in the image B is the ground truth, and the C is after we run the algorithm. That's the predicted contour. If we compare the black contour in the image B and C, that's going to be our error. And I have 3 box plots to show the error. The first box plot, if only the pulling deformation is introduced in our experiments, we can see both the deformable and rigid registration method both yields very good results. They are all the millimeter level accuracy. But once the tumor shrinkage is introduced to the pork towns, the difference appears. Only the deformable image registration method still maintains at its sub-millimeter accuracy level. And we notice that the results, the error from the deformable image registration method decreases while more number of markers is used. And this number is detected up to 10. So 10 markers yields the best results. Just want to mention this 10 marker comes from, this number comes from an empirical result to prevent the mutual marker interference. While we are using 10 markers, we also compare the error results from the deformable and rigid registration and also the surgeon's prediction. As you can see, our proposed deformable image registration method even outperforms the experienced surgeon's manual prediction. The second experiment is we want to prove the feasibility of the supervised autonomous tumor resection using the proposed marking and tracking method. The experiment steps are almost the same: tumor contours, and then dispense markers, simulate tissue deformation, manually pair the markers, reduce tumor bed, give the 5 mm offset, generate 3D path, control the robot to cut, and we compare the difference between the cut path and the drawn contours. Those three experiment results are shown in this slide. We highlighted in the left images. We highlighted the ground truth of the deformed tumor shape. On the right and on the right images, we highlighted the actual cutting path. By comparing them, their difference should be on the predefined 5 mm, and it's pretty close. So we proved that we successfully achieved sub-millimeter accuracy in this supervised autonomous tumor resection. Right, finally, the conclusion and future work. We first proposed a near-infrared fluorescent marking and landmark-based deformable image registration method to predict oral squamous cell carcinoma contours in sub-millimeter accuracy. What's more, we integrate this proposed marking and tracking algorithm into our robotic system and achieved and performed supervised autonomous pseudo-tumor resection. And then to go to patients, I want to highlight why we are here today. By achieving more accurate results, even than an experienced surgeon, we can get less recurrence rates, less post-surgical organ dysfunction, shorter rehabilitation, and higher survival rates. What's more, all these improvements on the surgical outcome is independent from individual surgeons' techniques, training, or experience, which means even a new surgeon can do as well as an extremely experienced surgeon. And lastly, we reduced the surgeon's labor as well. We switched their role from an operator to a supervisor. For the future work, first in the future we will do 3D deformable image registration rather than we register the tumor bed in 3D and overlay them, map them back to 3D and control the robot. And in the future we will introduce the oral space limitations rather than just asking the robot to cut from the top, which should be the cranial or the jaw, depends on the patient's locations. And what's more, currently we only ask the robot to cut the tumor, the pseudo-tumor, but without completely remove it. In the future we will figure out how to realize this 3D tumor removal. And it's my reference. Any questions?
Since we're a little bit over time, maybe then thank every speaker in the session and move on to the next session. Thank you.